will continue our discussion on affinity laws and specific speed, but as I said that before I go to discuss about the affinity laws, we have tried to analyze one another important aspect of fluid flow through any closed conduit is the dimensional analysis, that is Buckingham-Pai theorem. So, today we will work out a case when fluid is flowing through a pump, and if we apply Buckingham-Pai theorem, then what are the pi terms or the dimensionless term we can obtain, and from there we will see that from those pi terms we will try to explain what are the affinity laws. That means, if we know that one pump, maybe it radial flow pump or axial flow pump, whenever one pump is rotating at a given speed, and if we get a particular discharge and head at that speed or at that rated speed. Now, if you would like to quantify the another I mean, if you would like to quantify head and discharge at another speed, at a different speed than the rated speed, then how we can quantify without doing any experiment, because it is not possible to carry on rather to do experiments at each and every time, rather it is not possible to test at each and every speed to quantify the head and discharge. So, using affinity law we can predict that what would be the head and discharge if we know the head and discharge at any rated speed. So, as we have understood that before we go to discuss this, we now need to know what are the dimensionless term we can form whenever liquid is or fluid is flowing through a pump. And to do that, we have discussed about Buckingham-Pai theorem, and yesterday we have discussed about the theories, I mean what are the procedures of applying Buckingham-Pai theorem, and also we have discussed some useful relationship. So, today we will consider that whenever a fluid is flowing through a radial flow pump. So, let us say a fluid or an incompressible fluid, fluid is flowing through the impeller of a radial flow pump, or any pump rather, of a impeller of a pump. Now, what are the variables involved with this, and out of this variable what would be the repeating variables, and what are the what fundamental dimension we will consider to obtain the pi terms, that we will work out today. So, whenever an incompressible fluid is flowing through the impeller of a radial flow pump, we can list down the list of variables. So, if we recall that yesterday we have discuss about the procedures stepwise. So, initially as a first step we need to list down the variables involved with this case. So, number 1 is list of variables. So, list of variables we need to know. So, what are those? One is D, that is impeller diameter, then speed of the pump. We have discussed about an incompressible fluid, so maybe density of the fluid is rho, viscosity is mu. Then we can consider, as I discussed, that instead of considering H as a separate variable, because in most of the fluid machines fluid is flowing through a closed conduit, so it is not an open surface flow. So, we can club together G and H, and that will help us. So, we can consider G into H. Also, we can consider E, that we have written that E is energy per unit mass of the fluid, and of course that is P power, and these three variables, that is D N P, D N rho, mu, G H, E and P. So, these are the variables we can consider. Also, one another important quantity that we didn't write till now, that is Q, because Q is very important, we need to know, that is discharge. So, head discharge speed and then diameter of the, so diameter of the impeller D. So, we now listed down the variables. The next step is, what is the next step? If you can recall, that we need to find out the list of variables and as well as their dimension. So, if I now write in a tabulate form, so we will write this. So initially variable we are writing variables, then their unit, and another important thing is, as I discussed, we need to follow fundamental dimension either MLT or FLT, whatever it is. So that is dimensions. So these three are very important before we try to figure out a few pi terms or dimensionless term using Buckingham pi theorems. Dimensions. So the first quantity is Q. So if I write Q, that is discharge, of course unit is meter cube per second. Unit is meter cube per second. So Q is discharge, unit is meter cube per second, and what would be the dimension? If we follow MLT, suppose we are following fundamental dimensions, we are following fundamental dimensions MLT we are following for this case. So if it is m meter cube per second, then it would be L cube t to the power minus 1. So this is the dimension for this quantity. So this is about Q. Then another quantity is, let us say, speed, because initially I will list down the three important quantity Qn and of course Gh. So n is RPM, unit is RPM, and dimension should be t power minus 1. Then we have G into H together. So this is again meter square per second square. This is meter square per second square. So it would be L square t power minus 2. So this is the dimension G into H. Now next is diameter of the impeller D, and unit is meter. So this is L. Then what else? Q, N, G, H, D we have taken, Q we have taken, G, H we have taken, N we have taken. So remaining is rho, density. So this is diameter, this is speed of the pump, and this is the energy, we can say rather. Now this is density. So density, what is the unit? Density is kg per meter cube. So it would be m L power minus 3, m L power minus 3. Then mu, viscosity, what is the unit? Pascal second, that is m L power minus 1 t power minus 1. So this is the, we can, so rho is done, mu is done. Now total is P, P is power, this is power, that is watt, and unit should be m L square t power minus 3. Then remaining is E. Remaining is E. E, that is energy, that is known as energy per unit mass of the fluid. So this is energy per unit mass of fluid, and this unit should be meter square per second square, and you will get L square t power minus 2. So we have listed down the variables we have written their units and we have written also the dimensions following a fundamental dimension MLT. Now, so this is the first step that we have carried out. So, next, what is the next step? If we follow the yesterday we have clearly written the procedure of Buckingham pi theorem, then what are the next step? Next step is we now need to select 3 repeating variables. We now need to select 3 repeating variables, none are dimensionless and each with different dimensions. So, if we follow our previous lectures where we have listed down the procedures, the steps, then after listing down the variables, writing their unit and dimensions, now we need to select following the fundamental dimensions MLT. Now we need to know what will be the repeating variables. While we are selecting repeating variables, I am writing while we are selecting repeating variable, this is very important, repeating variables, non-dimensionless and each having and each with different dimensions, each with different dimensions. So, this is very important. So, while you are selecting repeating variables from these variables, we need to consider that none are dimensionless and each of them will be having different dimensions. Now, from these we can select 3 repeating variables and these repeating variables will appear in each pi term. So, we need to now select repeating variables and then these repeating variables should appear in each pi terms. So, here what are the total variables, that if we know m. So, m is the number of variables total, n is the number of total variables. So, n is the number of variables is equal to how much? We are having total 8. So, here we are having total variable 8 and we need to select m, that is m is number of fundamental dimensions, number of fundamental dimension. So, we have 8 variables and number of fundamental dimensions are 3 MLT. So, we will get n minus m, that is we will get 8 minus 3, that is we will get 5 pi terms or 5 dimensionless terms. We will get 5 number of or 5 pi terms or 5 dimensionless term. So, now what we have to do, that we need to select repeating variables and we will go to our next slides. So, out of these 8 variables, we are now selecting repeating variables. Criteria is that none are dimensionless and each with different dimensions. So, we are selecting repeating variable variables, we are selecting for this particular case as d, diameter of the impeller, speed and rho, density. Note that all these repeating variables will appear in each and every pi terms, and here every variable, I mean repeating variable is not dimensionless, they are having dimension and their dimensions are not equal. So, diameter is meter, speed rpm t power minus 1, density kg per meter cube. So, their dimensions are completely different and all are dimensional. So, we now need to proceed towards obtaining a few pi terms, and the number of pi terms that we are expecting to get from this exercise is 8 minus 3, that is 5. Okay. So, now question is, while we are selecting these repeating variables, note that here these repeating variables are geometric variables, flow property and fluid property. So, here we have selected 3 repeating variables. One is geometric, geometric variable, that is diameter, fluid property or flow property. So, these 3 very important, diameter, density and the speed. So, these 3 repeating variable d, n and rho, and then we need to follow another step. What is the next step? Then the first pi term can be expressed as a product of these repeating variables. If I can recall the steps number 4, that the first pi terms, suppose I would like to have first pi terms pi 1, this is the first pi term, this first pi term can be expressed as a product of repeating variables, each with but each raised to an unknown exponents. So, I am writing the first pi term, again I am writing the first pi term can be expressed as a product of repeating variable and each raised to a component, each raised to an unknown component, to an unknown component, and another variable that is very important, raised to a known component, raised to a known component, say 1, known component say 1. So, we have 8 variables and we have considered 3 repeating variables. So, we are left with 5 variables, that is we can form 5 pi terms. So, while you are forming pi terms, this pi term can be expressed as a product of repeating variables, each raised to an unknown component, let us say a1, b1, a1, a2, a3 or x1, x2, x3, whatever it is, that is up to you. And another variable we need to take out of this 5 variable, we need to take another variable that will raise to a known component, let us say 1. So, this is this pi 1, let us say I would like to say pi 1. So, if I go back to my previous slide and then say I would like to say pi 1. So, here d n and rho, d n without d n rho, there are 5 variables. So, if I take first pi terms as a cube, then q dimension is L cube t power minus 1. So, L cube t power minus 1. So, if I write 5 first pi terms, then pi 1 is equal to L cube t power minus 1, that is another variable, that is known variable raised to a component, let us say 1. And while forming the pi terms, this can be expressed as a product of these 3 repeating variables, while d, n and rho. So, what is the unit of d? L, L to the power, let us say unknown component x1, then n t power minus 1 into t power minus 1 to the power, let us say unknown component x2, and rho, that is m L power minus 3 to the power x3. So, where x1, x2 and x3 are the unknown component. So, while forming pi terms, this can be expressed as a product of these 3 repeating variables d, n and rho, each raised with an unknown component x1, x2, x3, and other variable, that is q, that is what we would now like to express in terms of pi terms, and that will raise to a component known component, say 1. So, now how we can proceed? So, this pi term is again, see, that will be m, I mean this is again a dimensionless. So, no dimensions. So, this will be equal to fundamental dimension m to the power 0, L to the power 0, t to the power 0. This is dimensionless term, and that will be equal to L cube t power minus 1 L x 1 t power minus 1 to the power x 2 and m L t power minus 3 to the power x 3. So, pi term is a dimensionless term and that would be m power 0 L power 0 t power 0 and other right hand side the term, the known variable, the other variable is which is raised to a component which is known, that is 1, other repeating variables are raised to an unknown component x 1 x 2 x 3. This is very important. So, now this is done. Now, what we need to do, this next is very important. So, we have now expressed that what would be the first pi terms and we have followed the procedure. So, what will be the now next step? Next step is considering dimensional. So, this is very important, this is very important. So, this is very important. So, what you have to see now I am writing considering dimensional homogeneity, because left hand side is m power 0 L power 0 t power 0, right hand side is also having m L t with some other unknown components, let us say x 1 x 2 x 3 or I do not know, that we need to know. So, considering dimensional homogeneity of both sides what we need to do, both sides of, let us say both sides of this is equation I am telling 1 of equation 1. So, considering dimensional homogeneity of both sides of equation 1 and equating the power of each of MLT we get, and considering dimensional homogeneity of both sides of equation 1. So, we are considering that equation 1 left hand side and right hand side is having dimensional homogeneity and equating the powers of each m L t we get. What we will get? That is what we need to know. So, how we can proceed? So, now see, if we are considering dimensional homogeneity and then what we will do, we will equate the power of each m L t in both the sides. So, left hand side power of m is 0. So, if I now equating power of m, so equating power of m, equating power, then left hand side is 0 and right hand side is x 3. So, this simply gives x 3 equal to 0. Now, equating power of L, then left hand side is 0, right hand side is that is, this is L cube, not L 3, this is L cube, I have written suffix 3, this is L cube. So, L cube to the power 1, that is L cube to the power 1, that is 3, I mean we have to equating the power, plus x 1 minus 3 x 3. Since x 3 itself is 0, so from here we get 3 plus x 1 will be equal to 0, this will give x 1 equal to minus 3. So, while we are equating power of L at both the sides, then we are getting x 1 is equal to minus 3, equating power of m we have obtained x 3 is equal to 0, now equating t. So, equating powers, left hand side is 0 of course, no doubt about it, and right hand side is how much? Minus 1 minus x 2, and then we get x 2 is equal to minus 1. So, we have obtained x 3 is equal to 0, x 1 is equal to minus 3, x 2 is equal to minus 1. So, now I am going to the next slides again. So, we have obtained, while we are trying to obtain first pi terms pi 1, we have obtained x 1 is equal to minus 3, x 2 is equal to minus 1 and x 3 is equal to 0. So, these 3 exponents we have calculated from this Buckingham pi theorem, and then pi term which is dimensionless, and that we expressed in terms of m power 0, l power 0, t power 0, that equal to l cube t power minus 1 to the power 1. This is nothing but q that we took while calculating or while trying to obtain the dimensionless pi term, that into d n rho to the power x. So, if I go back to my previous slide, d to the power x 1, that is l to the power x 1. So, that is d to the power x 1, then this is n to the power x 2 and rho to the power x 3. So, that is what we obtained, that is what we wrote in the previous slides. So, this first pi term pi 1, now x 1 is equal to minus 3. So, I can write this is cube into d 1 to the power minus 3, n 1 to the power minus 1, rho to the power 0. So, that means pi term, the first pi term will be cube divided by n d cube. So, this is the first pi term that we obtain from this by Buckingham pi theorem, that q is equal to pi 1 is equal to cube by n d cube. This is having one particular name. We will discuss what is called, this is called flow coefficient, this is q q by n d cube, that is called flow coefficient. This term known as pi term is known as phi, or it is known as flow coefficient. So, the first pi term that we obtain pi 1, that is q by n d cube, that is expressed in terms of that we call phi, that is flow coefficient. Similarly, we can again follow the same step and we can arrive with the other pi terms. So, let us now try to do how we can obtain another 3 pi terms, I mean 4 pi terms, because we will obtain total 5 pi terms. So, first pi terms we obtain. For the second pi terms, I am not going to explain each and every again step details, but let us say second pi term pi 2, I am writing that second pi term will be which one, that will be which one. So, second pi term will be, if I go to my previous slide, we have taken cube, d n rho are the repeating variables, so we need not to take, so we can take g into h. So, I am taking g into h. So, g into h, what is the unit? So, L square g into h L square t power minus 2. So, this is raised to the known coefficient, let us say 1, into again d to the power x 1, that is L to the power x 1 and t power minus 1 to the power x 2 and m L minus 3 to the power x 3. That is what we will obtain. So, while you are obtaining second pi term, that is g into h, this is g into h, this is g into h. So, what you have to do, pi 2 is a dimensionless term. So, that is essentially equal to m power 0, l power 0 and t power 0. So, now what we have to do, we have to equate, we have to consider the dimensional homogeneity at both sides of the equation and equating power of each m, l and t. So, if we equate power of m, l, t, then again for m equating power, that means if we equate the power, so right hand side is 0 and left hand side is x 3. So, x 3 will be equal to 0, then L equating power, right hand side is 0 and left hand side is 2 plus x1 minus 3x3. So, this will give x3 is equal to 0. So, this will give x1 is equal to minus 2, x1 is equal to minus 2, and if we equate power of t, then 0 is equal to minus 2 minus x2. So, x2 is equal to minus 2. So, we are obtaining x3 is equal to 0, x1 is equal to minus 2, x2 is equal to minus 2. So, what will be the pi term? So, the second pi term, that will be pi 2 will be g into h into L minus 2 t power minus 1 into minus 2 into this term is 0, sorry, I am writing in a different form rather, into d to the power minus 2 and n to the power minus 2 and rho to the power 0. So, this will give pi 2 is equal to g h by n square d square. So, this is very important that another pi term we have expressed, pi 2 is equal to g h by n square d square, and g h by n square d square, this pi term is I mean again is a outcome of dimensional Buckingham pi theorem. So, we will write this pi term as g h by n square d square. So, we have obtained first pi terms and we have obtained second pi terms g h by n square d square. We have to proceed again to obtain another 3 pi terms, that is of course, we have taken q and g h. So, we are left with mu, e and p. So, we have to obtain another 3 pi terms. Mind it, we have said that it is not always possible that we will get pi terms, maybe multiplication of each pi terms we need to multiply with another. So, we will get pi term, that some useful relationship yesterday we told that any pi term can be expressed as a function of other pi terms by multiplying any numerical constant also. So, for the time being we have obtained 2 pi terms, one is q by n dq, that is flow coefficient, another pi term that we have obtained, that is g h by n square d square, this is we have expressed. So, we will now proceed to obtain another pi terms, let us say if we consider e or p. So, another pi term p3, pi 3, that is equal to, let us say we are considering power is equal to what, that is equal to how much, m L square t power minus 3, and known is variable raised to the power 1 m L square t power minus 3, that will be L1 to the power x1 into t power minus 1 to the power x2, and that is m L to the power minus 3 to the power x3, that is rho. So, and this is again a dimensionless term. So, this is m power 0, L power 0, t power 0, and if we equate each and every terms, I mean we have to consider dimensional homogeneity at both the sides, and we have to equate powers of m L t, and if we equate that, so now equating m power, so equating power, m, then what you obtain, right hand side is 0, left hand side is 1 plus x3, that it will give x3 is equal to minus 1. If we equating power of L, then right hand side is 0, left hand side is 2 plus x1 minus 3 x3. Therefore, from what we get, twice plus x1, x3 is equal to minus 1, that is plus 3 equal to 0, which will give x1 is equal to minus 5, x1 is equal to minus 5, and t equating power, right hand side is 0, left hand side is minus 3 minus x2, therefore, x2 is equal to minus 5, we obtain from there x2 will get x2 is equal to minus 3. So, we have obtained this value. So, if we write pi 3, this pi 3 is equal to p, that is this term is for p into d to the power x1 minus 1, then n to the power x2, that is x2 is equal to 3 and rho to the power x3 that equal to x1 is equal to minus 5 d1 to the d to the power minus 5 n to the power x2 is equal to 3 and rho to the power x3 that is minus 1. Therefore, that is equal to p by rho d to the power 5 n to the power x2 is equal to x2 is equal to minus 3 x2 is equal to minus 3 x2 is equal to minus 3, so minus n cube. So, we have obtained another pi term, pi 3 is equal to p by rho n cube d to the power 5. This is known as power coefficient or coefficient of power, whatever it is. So, rho p by rho n cube d to the power 5, this is known as power coefficient or coefficient of power. So, this is known as power coefficient or coefficient of power, that is power coefficient. So, we have already established 3 different pi terms, pi 1 flow coefficient, then gh by n square d square and p by rho n q d to the power 5, that is power coefficient. So, we have expressed 3 different pi terms. So, we are left with another 2 pi terms that we need to establish. Gh pi 2 by pi 1 can be expressed as a some other quantities, as I said you that yesterday we have written some useful relationship. Any pi term can be expressed by power of other pi terms. Any pi term can be multiplied by any numerical value to obtain another pi term. Any pi term can be replaced as a function of another pi term. Okay. And then we will obtain pi 4 if we consider now E. So, what is the unit of E? L square t to the power minus 2, L t to the power minus 2 to the power 1 and L to the power x1, t1 minus to the power x2 and m L minus 3 to the power x3, and that will be again dimensionless, m power 0, L power 0, t power 0, t power 0, that is t power 0. As I said that we need to consider dimensional homogeneity and then we have to equate power. So, if we consider power m equating power each sides of these equations of m, then what we will get? 0 right hand side, left hand side is equal to x3, therefore, x3 is equal to 0, L equating power right hand side 0, left hand side 2 plus x1 minus 3x3, that will give x1 is equal to minus 2 and t equating power, and that will give 0 right hand side and left hand side minus 2 minus x2, therefore, x2 is equal to minus 2. So, we are getting this. So, we are now obtaining pi 4 that equal to E d to the power x1 minus 2 n to the power x2 is equal to minus 2 and rho to the power x3, that is 0. Therefore, we obtain pi 4 is equal to E d to the power minus 2 n to the power minus 2, therefore, E by n square d square. So, this is d is equal to we are obtaining E by n square d square. So, now this is as I said you that E by rho and n square by d square. So, that may not be we need to multiply with another numerical value, or we need to express in terms of different other pi terms, other pi terms. So, we have obtained pi 4 is equal to E by n square d square, and we are left with only mu. So, I am writing pi 5 that equal to mu unit is m L power minus 1 t power minus 1 to the power 1 into d L power x1 t power minus 1 to the power x2 and m L power minus 3, that is rho to the power x3, and that equal to m power 0, L power 0, t power 0. So, again we are considering dimensional homogeneity and equating power of each m L t and both the sides. So, what we get if we equating power of m, equating power. what we will get if we equating power, then right hand side is 0, left hand side is 1 plus x 3, that is x 3 will be minus 1. Then if we equating power of L, equating power of L, then we will get right hand side 0, left hand side is minus 1 plus x 1 and minus 3 x 3, x 3 is equal to minus 1, that is minus 1 plus x 1 plus 3 equal to 0, which will give x 1 will be equal to minus 2, and ultimately t we have to equate, and we will get 0 is equal to minus 1 minus x 2, therefore x 2 is equal to minus 1. So, if we express pi terms pi 5, that equal to mu into d to the power x 1. So, d to the power x 1 is equal to x 1 is equal to minus 2, and then n to the power x 2, that is minus 1, and rho to the power minus 1. So, that is mu by rho n d, mu by rho n d, sorry, d to the power d square, rho n d square, mu is by rho n d squared. So, now question is mu by rho n d square, reciprocal of this quantity is essentially Reynolds number, right. So, this is very important that this will give us the expression of Reynolds number. If we can rearrange this pi term, rho n d, n into rho v d. So, pi 5 is equal to mu by rho n d square, and this is essentially becomes Reynolds number, that I mean if I can write that in a bit different form, that I can write 1 by it. So, 1 by rho into n d into d divided by mu. So, reciprocal of this is essentially 1 by Reynolds number. So, all these pi terms, that is against a dimensionless term, from here it is clear that it essentially indicates that it is a Reynolds number. So, with this we have arrived a few pi terms. So, that is what I have exercised only to know how we can obtain a few dimensional term when from a flow through a pump, or it need not to be flow through a pump. Whenever fluid is flowing through a pipe or any closed conduit, if we know the variables, and from there knowing the fundamental dimensions and considering of repeating variables, we can form a few dimensionless term. And as I said you that pi 5 can be expressed in terms of 1 by Reynolds number. So, it is a dimensionless term. So, our interest is to obtain that out of this dimensional analysis, we have obtained a few pi terms. So, but our interest is only to obtain 3 important pi terms, that is very important for this analysis is of course f, pi 1, pi 2, pi 3, pi 4 and pi 5 are 0. That is what we have written, that will be functional relationship, and that will follow such that has to be 0. Now, our interest over here is that when we go to discuss about affinity laws, that f into pi 1 is cube by n d cube, and then gh by n square d square, and p by rho n cube d to the power 5, that equal to 0. So, this is our interest, that flow coefficient, power coefficient and gh by n square d square can be written in terms of other that is known as head coefficient. We can write that pi 2 we can call is head coefficient. This is flow coefficient, this is called head coefficient, and this is power coefficient. So, this is very important for pump because flow, head and power. So, now okay, we have obtained 5 pi terms, but out of these 5 pi terms we have express these 5 pi terms in terms of a few 3 important coefficients: flow coefficient, power coefficient and head coefficient. Now, knowing this, we can now proceed to obtain or with another arrangement of, or we can arrange with these pi terms, we can multiply each another or divide another and we can obtain another a few pi terms. So, now that I mean if data obtained from the test or model machines, if we obtain data from a model machines, and so that the variation of this dimensional parameter with one another, and suppose we are carrying out a test in a model machines to obtain the variation of this 3 quantity, and if we plot the graph, and that graph can be used, that graph whatever you obtain, that can be applicable to predict or the performance of any other homologous series, machines of belongs to homologous series. So, what I am telling, these 3 coefficient, flow coefficient, head coefficient, power coefficient. So, if we carry out test in a particular machines, in a model machines, and if we can obtain these 3 coefficients, and if we plot a graph, that graph can be used to predict the performance of machines of homologous series. So, this is very important. Now, as I said you that now we will slowly move to obtain the affinity laws. What is affinity laws? As I said you that whenever we carry out test in a model machines, it is not possible that we should carry out test at each and every machines. So, when you carry out test at particular machines, rather we consider a particular speed, and that we call it rated speed. So, whenever we run a machine at a rated speed, we obtain Q and H. If you would like to predict Q and H when machine will be operating different other speed than the rated speed, then is it possible to carry out test again? No, and that is why affinity laws are used, so that we can predict the head discharge capacity or performance of a pump when pump is running at a speed which is not exactly the rated speed, when the pump testing was done. So, whenever pump testing was done at a speed that is rated speed, we have obtained Q and H, and we have plotted a graph, and rather we have obtained flow coefficient, power coefficient, head coefficient, and from that graph we can predict what will be the head and discharge whenever machine is operating different other speed than the rated speed. So, and how we can predict, and that is governed by the affinity laws. So, now I will discuss about the affinity laws by knowing these 3 coefficient. Only to obtain these 3 coefficient, very important for the pump pumping system, pump operation, that is flow coefficient, head coefficient, power coefficient, and that is why I did this exercise, that is Buckingham pi theorem, how we can proceed, how we can analyze, or how we can obtain a few pi terms whenever fluid is flowing through a pipe. And now I am discussing about the affinity laws. So, what is the affinity laws? Suppose if I draw a H cube curve of a pump, suppose I am drawing a H cube curve of a pump, H cube curve. So, and whenever H cube curve I am obtaining, let us say this is the H cube curve I have obtained at a rated speed, let us say N1. So, this curve H and cube head discharge relationship that I obtain at this rated speed N1. Now, maybe we have obtained another head discharge characteristics which is when pump is operating at different rated speed N2. Suppose I have obtained another head discharge characteristics when machine is running at different speed at N2. Suppose this is at N2. So, if I know the flow coefficient, head coefficient and power coefficient, only we need to predict. Now, if we vary the speed, maybe if we close the discharge valve, or somehow for some reason we need to change the speed of the pump, then shall we get the same discharge or head? No, there will be a change. So, how we can predict whenever pump is running? It is not possible that whenever pump is running in a field or in an industry, how we can measure the head and discharge, but if we know this information, then we can predict, okay fine, if we reduce the speed of a pump by this much amount, by this then but by this magnitude, then what would be the head and what would be the discharge, whether that head or discharge is capable of meeting the demand of the system or not, that is very important. And we need to know whether that head and discharge is capable to meet the demand of the system or not, because sometimes it might happen that whatever discharge we are getting, whatever head we are getting, that it is not possible to supply that amount of fluid in that desired location, as a result of which there some undesirable phenomenon might occur. So, we need to know that even if we reduce the speed, that speed will be capable of having developing head and discharge from that pumping station, so that system demand can be satisfied. Okay. So, now if our system resistance curve is like this, suppose system resistance curve is like this, So, here is operating point, here is operating point. So, now suppose this is very important. So, if I know the head discharge capacity at a rated speed. So, suppose if I know the head discharge characteristics at rated speed, then if speed deviates from the rated one, then what will be the head and discharge developed by the pump. So, now what I will do, I would like to apply affinity loss. What is the affinity loss? Suppose we have obtained a few coefficient that is known as flow coefficient, head coefficient and power coefficient. So, I now would like to see, suppose I know the when operating point is here, let us say this is point A, I know the head and discharge whenever speed is N1. So, suppose speed is N1, I know the head and discharge at this point, it let us say QA, and this is head developed by the pump HA, and this is the H static, and this is the system resistance curve, this is system resistance curve, right. So, static height plus system resistance curve, and let us say rated speed, let us say N1. So, N1 is the rated speed at which I have tested the pump and I have drawn the HQ characteristics. And from the Buckingham pi theorem, I know there are a few coefficient that we have obtained. Flow coefficient that is phi, that is cube by n d cube. Then what we have obtained head coefficient, that is gh by n square d square, and power coefficient, let us say phi 1, phi 2 and phi 3, that is p by rho n cube d to the power 5. So, these 3 coefficient you have obtained, and when you are carrying out test of a model pump at a rated speed, if we calculate these 3 coefficient, if we plot the graph as I said, and then that graph can be used to predict the head discharge or performance of machines of homologous series. What do you mean by homologous series? Now, how we can predict? So, now if I would like to calculate that what would be the discharge at if the machine is running at a speed which is not the rated speed, let us say N2. Suppose I would like to obtain the head discharge characteristics when machine is running at N2, at the speed N2, which is not equal to where N2 is not equal to N1, that is when we are deviating from the rated speed, then how we can predict the head discharge characteristics. So, from equality of pi terms, so I know that if we equal the pi terms q by n d cube, so Q1 homologous series machine of same size, not impeller of same shape, maybe size is different. So, this is called homologous series. I mean, when you are considering maybe impeller of a circular shape impeller, so we might change diameter, but its shape is remaining same. So, it belongs to the homologous series. So, if for a given pump, I mean even if it is not given pump, if d is changed, then you still can calculate, but for a given pump, so for the time being what the problem we are going to discuss, maybe the given pump it is operating in the same system. So, diameter d will remain constant. So, then N1 by d cube is equal to Q2 divided by N2 into d cube, because pump is remaining same pump. So, diameter of the impeller will remain same. So, from there we can tell Q1 by N1 will be equal to Q2 by N2, right. So, this is we are obtaining from the flow coefficient, because that will remain same for homologous machines. The machine belongs to homologous series. Here the same pump d is not going to change, rather shape is remaining same. So, I can apply this and I am obtaining. So, now if I know Q1 at a speed N1, now if I change the speed to N2, then I can calculate what would be the Q2 at which is running at different speed N2, that will be N2 by N1 into Q1. So, this is the head that will be developed by the pump when the same pump or pump of homologous series is allowed to run at a speed which is now not equal to the rated speed. Very good. So, we have obtained about the information about the Q. Now, what would be the H? So, now again we have obtained another coefficient that is called head coefficient. This is head coefficient and this is called power coefficient. This is called power coefficient. So, we have obtained flow coefficient, head coefficient and power coefficient P by rho n cube d to the power 5. So, now if I apply again, so, G is remaining, D is remaining same. So, if I apply pi 2 terms, so if I apply now pi 2 terms, so equating now to obtain Q equating pi 1 terms. If I now equating pi 2 term, that is GH1 by N1 square D square is equal to GH2 divided by N2 square D square, because as I said you that pump belong if we can obtain these 3 coefficient from a model testing machine, from a model machine tested at a rated speed N1, then we can predict the performance rather other quantities of any machine belongs to homologous series. So, here diameter is not changing, so machine is remaining same. So, what we can predict is that now I can predict, suppose whenever machine is running at the end speed, suppose this machine is running at end speed and developing head HA. So, what would be the head being developed by the pump when it is running at N2, that we can calculate, because it is not always possible that the pump operator should have this curve and he will calculate from the curve itself. So, but by doing this analysis we can calculate that it would be H1 by N1 square will be equal to H2 by N2 square. Therefore, if I know H1 and N1, and if I now allow the pump to run at N2, then I can calculate H2, that equal to will be N2 square by N1 square into H1. So, this is the another relationship that we can obtain head developed by the pump H1. So, what will be the new head when pump is allowed to run at a speed which is not equal to the speed of the rated one. So, this is relationship 1 and this is relationship, let us say, or this is relationship A and this is relationship B. So, what we can say, from A we have obtained Q1 by Q2 is equal to N1 by N2, right. Q1 by, so we have obtained Q2 is equal to N2 by N1 into Q1. So, Q2 is equal to N2 by N1 into Q1, Q2, Q1 into Q1, and we have also obtained H2 is equal to N2 square by N1 into H1. So, we have obtained H2 is equal to N2 square by N1 square into H1. So, this is A, this is B. From these two relationships, what we can obtain, that H2 by H1 is equal to how much? H2 by H1 is equal to Q2 square by Q1 square. So, H2 by H1 square, H1 is equal to Q2 by Q1 square. Therefore, I can obtain H varies as Q square. From there we can obtain H varies as Q square. So, this is, and these are known as affinity laws of the pump. These are the affinity laws. So, that is, if we carry out test of a model pump at a rated speed, if we calculate these 3 coefficients, and now if you would like to allow, and if we plot these coefficient in a graph, and then that graph can be used to predict the performance of the same pump, or the pump belongs to homologous series when the pump is allowed to run at a speed which is not equal to the rated speed. And how we can calculate the head discharge when pump is running at a different speed, and that can be calculated using the laws which are known as affinity laws that we have derived. And we will discuss about a few important things from this expression that we have derived, that H2 by H1 is equal to Q2 by Q1 square, that is H varies as Q square, in the next class. I stop here today and I will continue in the next class. Thank you.